It started out with graphene and then it went to functions. I'm doing FOIL to solve X. Next is the expressions. Now I have to see if X is equal to or greater than 3.
This is the Chapter 4 practice test given out May 4th, 2021. Let's go over question number 1. According to an article on the Guardian website, a British woman born in 2003 has a probability of 0.27 of living at least 100 years. Suppose that we randomly selected 200 women who were born in 2003. Will exactly 54 of them live at least 100 years? Explain. So how do they get the 54? Well, if you take 0.27 and you multiply that by the 200 women they got, you will get the 54. But I'm going to underline that word exactly. Will you always get exactly that number? And the answer is no. That's a semicolon. Probability describes what happens just one time? No, happens in many repetitions, which is probably way more than the 200 of a chance process. And also to respond, we would expect to get, let me change my color, about or close to 54 women. Not exactly, that's why I underlined that word, who live at least 100, but exactly 54 is not guaranteed. Because you do this over and over and over again, you might get like 50, one other time you might get 65, but we would expect around 54. Okay, let's try example 1B. 5 high school friends all happen to be females born in 2003. Assuming that the survival of each one is independent, underline that word, of the others, what is the probability that at least one of them lives to be 100 years old? So there's 2 ways to do this one. I'm going to do the first one the easiest way. When you see this one, the word at least, you should think of the complement. Here is none of the 5 live. So let's just do the quick complement rule and then we'll figure out another way of doing this. So the first part you need to figure out is the what's the probability that none live to 100 years. And you can do some quick calculations that if it is 27% to live to 100, that means there's a probability of 0.73 to not live to 100 because those equal 1. Remember, yes, it's kind of like my idea, yes plus no equals 1. So that would be 0.73. And there's 5 of them, right? Because if you can also do that little line thing, right? Friend 1, 2, 3, 4, 5, and we're saying that none of them will live there. So that would be 0.73 to the 5th power. and you'll get an answer of 0.207. Okay, so to get at least one now, use a darker color. Come to me, purple, 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 purple. So the second part is then the probability that at least one of these lives to 100 years is using the complement, which is 1 minus the probability that none live to 100. So that'll be 1 minus 0.207, and then your answer is going to be 0.793. So that is our answer. Okay, so that's the easiest way of doing the complement. All right, the long way to think about at least one of them would be the probability that one of them gets it, probability that two of them live to it, probability of 3, probability of 4, and probability of 5. And I just want to show you what one of these looks like. Kind of painful, but you know, 0.27 that one person lives, and then 0.73 the other 4 don't live. Does this make sense? I'm just going to do one more. The probability that 2 of them live to 100, that means the other 3 would not. And then you would basically keep going and then just add up your probabilities. So that one's a little bit longer. That's why the complement's a little bit shorter.
Hello everybody, my name is Batman and I'm going to do this question on question number 2. So let's begin this question. Alright, here's question number 2. It's about the probability distribution for the type of vehicle chosen is given here. It's given as this chart right here. Anyway, in part A, it's asking, what is the probability that the vehicle is a crossover? How do you know? Well, it's asking for the probability that the vehicle is a crossover. And a crossover, it was a question right here, and for the probability, you're supposed to know, like, probability of crossover equals 1, meaning like 100%, because the chart is meant to be add up to 100%, and it's minus to, well, in parentheses, passenger plus pickup truck plus SUV and plus minivan. And all these numbers in, I guess, blue-greenish is supposed to be in the parentheses, and when I add them up, it's 0.76 in the parentheses, and when I subtract them, and it equals to 0.24 or 24%. And that's how I got the answer in this chart right here in red. Alright, in part B, it's asking, given that the vehicle is not a passenger car, what is the probability that it is a pickup truck? Well, at first it says, given that the vehicle is not a passenger car. It's given that we should know what the probability of a not a passenger car is. So it's this, and it's 1 minus the probability of the passenger car, because, well, yes plus no equals 100%. I don't know what I'm saying right now. So for a probability of passenger car, it's a 0.46, because right here it says it in the chart. Well, if you subtract 1 minus 0.46, then it will be 0.54. It equals 54%. But we're not done yet. It's also asking, what is the probability that it is a pickup truck? So what do we do here is that we should solve the probability of a pickup truck and a not a passenger car. So what we do here is that a pickup truck is a numerator, which is 0.15 in this chart. So that's how I got it right here. And not a passenger car, it's 0.54. So I put that as a denominator. And when you divide them, it's 0.278 or 27.8%. For part C, what is the probability that the vehicle is a pickup truck, SUV, or minivan? So what we do here is that we should put this probability of pickup truck, SUV, or minivan. But there's a key word to this. It's or, meaning that we can add up all three of those. So 0.15 plus 0.10 and plus 0.05. And how I got it? It's right here. 0.15, 0.10, 0.05 for pickup truck, SUV, and minivan. And when you add them up, it's equal to 0.3 or 30%. And finally, part D. Suppose you select 3 vehicles at random. You want to know the probability that the vehicles are of 3 different types. Describe how you would carry out a simulation to help answer this question. Do not actually perform the simulation. Okay then. Alrighty then. I don't know what the last part is meant to be. You want to know the probability that the vehicles are of 3 different types. So the question you're trying to ask is, what is the probability that the vehicles are of 3 different types? That's the state for this part right here. After that, they're trying to make us do the DARE strategy. The D is the digits, A for assign, R for repeat, and E for the end. For digits, I put numbers 1 through 100 just because this is trying to add up to 100%. So like 1% through 100%. Passenger car, it's 1 through 46 because 46 numbers or 46%. Then another 15 numbers, 47 through 61 for pickup trucks because of this. Then adding up 10 more numbers, 62 through 71 is for the SUV right here. Crossover, you add up 24 more numbers, 72 through 95. You can already guess what I'm trying to say here. And finally, minivan, 5 more numbers, 96 through 100. Well, for assign, we're supposed to use a random number generator. You're supposed to generate from the arrangement of 1 through 100, and it just randomly generates for you. Hey guys, it's me again, and I just want to clarify about my mistakes and what I put in this last part. I didn't know about the assign part, and the random number generator part is supposed to be part of the conclusion. The assign part was supposed to be about the numbers of the passenger car, pickup truck, SUV, crossover. It's supposed to be related to what is above, like in the digits part. So please disregard of what happened and back to the video. For repeat, we're supposed to skip repeats because why would you generate the same number in one group? It doesn't make any sense. For the end, You're supposed to end that random generator if you're done selecting 3 different numbers from one group. The reason why I do this dare strategy is so that I can record the 3 numbers corresponded to vehicles of different types. I would perform many repetitions of this process and calculate the proportion of times where the 3 vehicles were different types. And that is the answer for part D. And yeah, that's pretty much it for question number 2.
Hello everyone, my name is Mooney and I am president of Mooney Nation. So today I will be teaching you guys how to answer question 3, which is taste test. Our question reads, Ivy conducted a taste test for 4 different brands of chocolate chip cookies. Here's a two-way table that describes which cookies each subject preferred and that person's gender. Suppose one subject from this experiment is selected at random. So the first thing we will do is look at our two-way table, which is separated by cookie brands and gender. I also went ahead and took a total of all the cookie brands and the gender. Now that we know what our two-way table looks like, we will answer question 3A, which is find the probability that the selected subject preferred brand C. To solve this question, we are going to find the probability of C, which will give us a numerator of 24, because that is the total subjects that preferred brand C, and a denominator of 94, because that's the total subjects in general. So whether they're female or male, or whether they preferred A, B, C, or D for a cookie brand. This will give us a probability of 0.255. Our next question is 3B. Find the probability that the selected subject preferred brand C or is a female. So to solve this question, we will be using the general addition rule, which is probability of A plus probability of E minus probability of A and B. So our A in this problem is brand C, and our B in this problem is female. So what we're going to do is we're going to have 24 over 94 plus 36 over 94 minus 13 over 94. This will give us 47 over 94, which will ultimately give us probability of 0.50. Our final question is question 3C, which reads, find the probability that the selected subject preferred brand C, given that she is female. So for this question, we're going to use the formula for conditional probability, which is probability of A given B equals probability of A and B over probability of B. So our A in this formula is brand C, and our B is female. So for our numerator, what we're going to do is we're going to refer to our two-way table, and we're going to look at a female who preferred the cookie brand C, which is 13. And our denominator will be the total females, which is 36. This will give us a probability of 0.361. I hope this video was helpful in solving question 3. See you next time.
Hello, my name is Kat, and I'm going to be showing you how to do question number 4.
Mike's Pizza. You work at Mike's Pizza Shop, and you have the following information about 7 pizzas in the oven. 3 of the 7 have thick crust, and 2 of the 3 thick crust pizzas have mushrooms. Of the 4 remaining pizzas, 2 have mushrooms. Choose a pizza at random from the oven. Part A asks us to make a Venn diagram to model this chance process. Pizzas are grouped together based on whatever toppings they have. The part where the 2 circles meet represents the pizzas that have both mushrooms and thick crust. We are already told that out of the 3 thick crust pizzas, 2 of them also have mushrooms, meaning that 2 should be in the center. Knowing that there are 3 thick crust pizzas in total also reveals that there should be a 1 in the circle with only pizzas with thick crust. 2 of the remaining 4 pizzas have only mushrooms, and with this we can eventually figure out that the remaining 2 pizzas have neither thick crust or mushrooms. Using this completed Venn diagram, we'll be able to solve part B, which says, are the events getting a thick crust pizza and getting a pizza with mushrooms independent? Explain. Basically, the question is asking us, does getting one pizza affect the chances of getting another?
Knowing this, we should try to find the probability of getting a thick crust pizza given that it has mushrooms, and then a thick crust pizza given that it has no mushrooms. We need to find the probability of both in order to know if they affect each other. Out of the 4 total pizzas with mushrooms, only 2 also have thick crust, meaning the probability is 2 out of 4. We could see the number of pizzas with no mushrooms just by looking at the numbers 1 and 2, the 1 from the thick crust circle and the 2 outside of both circles. The 2 and the 1 combine together to represent the 3 total amount of pizzas with no mushrooms at all, meaning that the probability is 1 out of 3 because only 1 of the pizzas without mushrooms has thick crust. If both probabilities were to be equal, then these events would be independent because they wouldn't affect each other. However, these probabilities are not equal, therefore these events are not independent. Part C says, you add an 8th pizza to the oven. This pizza has thick crust with only cheese. Now, are the events getting a thick crust pizza and getting a pizza with mushrooms independent? Explain. In our new Venn diagram, the thick crust circle now has a 2 representing the pizzas with only thick crust. Just as we did for the last question, we have to look for the probability of thick crust pizzas given that they have mushrooms, and the probability of thick crust pizzas given that they have no mushrooms. Using our Venn diagram, we're able to figure out that both probabilities are 2 out of 4, meaning that the probabilities are equal to each other, meaning that these events are independent from each other, meaning they don't affect each other. Thank you.
So it's 1 in the morning while I recorded this, but hi, my name is Dr. Spencer Reed, and I will be presenting problem 4, which is titled Exercise Matching Socks. I hope you enjoy it, and I hope you learn something. Don't judge the low quality. Bye! Okay, so this is problem 4. The name is Exercise Matching Socks. It is presented by Dr. Spencer Reed. Okay, so the problem reads, Gabriel is not one for pairing his socks before he throws them into his sock drawer. One dark morning, his sock drawer contains 8 blue socks, 6 brown socks, and 4 gray socks, totaling up to 18 socks. He pulls 2 socks out at random without looking at them. Okay, so we know that his sock drawer contains 18 socks. So question A asks for, what is the probability that both socks are blue? Okay, so I will be beginning with the formula, which is over. Okay, so we're gonna put on this top line 8, and then on this bottom one we're gonna put 18. Why, you may ask why I'm putting those numbers. The first one, I'm putting it because it corresponds with, it corresponds with this. And then this is just the total of socks. So we're gonna name this sock 1, sock 2. And this bar we're putting sock 7 over 17. And why, you may ask? We're putting that because it's just the chance number. And then we're gonna multiply these, which is 56. You feel free to pull out your calculator if you need to. But we're basically multiplying 8 plus 7, which equals 56. And then 18 plus 17, which equals 306. And then we're converting it into decimal form, which is 0.1883. The way I got that was just by putting in the numbers into my calculator and removing the decimal and whatnot. Okay, so the next question reads, what is the probability that that 2 socks are the same color? Note, his drawer contains 8 blue socks, 6 brown socks, and 4 gray socks. So this information is important because it's asking you how they may be the same color. Okay, so I'm going to start with my formula. Classic P, 2 socks that are the same color, because that's what we're aiming for, remember. And then I'm going to put P, 2 blue socks. Okay, I'm running out of space. And then we're adding plus P, brown socks. So we're listing every color that we have, so which is blue, brown, and gray. And then we're putting 2 gray. And remember, we're not putting 8 blue socks or 6 blue socks or 4 gray socks, because remember that we're trying to aim for 2 socks, a pair of the same color. So from here we have to figure out what our probability on 2 of the same color would be. So then I'm going to write it down in the formula, which, bear with me, let me pull out my pen. So it's going to be 8C2 over 18C2 plus 6C2, 18C2 plus 4C2, 18C2. Okay, I'm replacing the numbers of our original socks, which were 8, 6, and 4, into this. And remember that this piece is the total of our sock drawer. And this is each individual color. So from there on, we are going to how do you say it? Addition. Okay, so bear with me. I'm sorry. I'm having difficulty issues, or connection issues, I guess. Okay, so from here on, we are going to see which event is more likely, which, I guess, sock color is more likely to happen. So from here on, we are converting these formulas into decimals. So, excuse me. So from here, it's going to be 0.183 plus 0.098 plus 0.39 plus 0.32. And remember, we're just converting this into this. It's not that hard. Oh, I'm sorry, this. Okay. So there are 2 ways to solve this, which is, I'm just going to show you the general one, which is using this formula, and then plugging this, I'm sorry, I'm just going to pull it down here, 5/6 over 306, and then we're going to plug in our numbers, which were 6, representing the 6 brown socks, over 18, because remember 18 is our total, and then 5 over 17, which was our brown, I guess, and then we're gonna add this plus 4, 18, 13 over 17. The 4 and 3 are basically the 7, I guess. Okay, and then this would equal 0.32 in the decimal form. Let me show you the other way that we could solve this. I'm just gonna have to turn over my page, so bear with me. I'm sorry, this is taking too long. So then we're going to use our tree diagram. So it would be this. So now I'm going to write this over here. Yeah. Like I said, I'm just transferring this diagram onto my paper. And let me turn it back so I can write the, formula forms. So it is going to be A over 18 parentheses 7 over 17, again parentheses, plus 6 over 18 parentheses 5 over 17 parentheses plus 4 over 18 plus 3 over 17 parentheses. Okay, so then we're going to convert this into decimal form once again. 83 plus 0.098 plus 0.039 equals 0.32. I'm sorry for the length of this video, but I hope you enjoyed, and I hope you learned something. Yeah, thanks for watching. Let me try to focus this. Okay, bye.
Hello, my name is Wendell Chendel, and today I will be reviewing Chapter 4, Probability of Question 6, Detecting Steroids. Detecting steroids. A company has developed a drug test to detect steroid used by athletes. The test is accurate 95% of the time when an athlete has taken steroids. It is 97% accurate when an athlete hasn't taken steroids. Suppose that the drug test will be used in a population of athletes in which 10% have taken steroids. Let's choose an athlete at random and administer the drug test. Part A. Make a tree diagram showing the sample space of this chance process. So 10% took steroids and 90% didn't take steroids. Now let's take a look at the 10% of those who took steroids. They can either get a positive test or a negative test. So 95% of those athletes who took steroids were accurate, which is the positive test, in which those who took steroids tested negative was 5%. Now let's look at the diagram below. 90% didn't take steroids. When an athlete hasn't taken steroids, it is 97% accurate for the negative test. And as for the positive test, it is 3%. Part B. What's the probability that the randomly selected athlete tests positive? There are two ways the athletes can be tested positive: by taking steroids or not taking steroids. So the 10% that took steroids tested 95% positive, in which you should multiply 10% and 95%, and the product of that is 0.095. As for the 90% who didn't take steroids, 3% tested positive. Multiply the 90% of those who didn't take steroids with the 3% that tested positive, and the product of that is 0.027. To find the probability of positive tests, add 0.095 plus 0.027 equals 0.122. Part C. Suppose that the chosen athlete tests positive. What's the probability that he or she used steroids? The fraction we're going to use is probability used steroids and positive tests over probability positive tests. In Part B, we have already solved the problem to find the positive test, which is 0.12. And the probability used steroids and tested positive was from the tree diagram we made earlier. The probability for that was 0.095. Divide 0.095 over 0.122. The quotient of that is 0.779. And that's the end of reviewing question 6, detecting steroids. Thank you.
All right, let's go down to question number 7. Many-sided die. The outcome of chance events in a fantasy role-playing game is determined by rolling polyhedral dice with anywhere from 4 to 20 sides. Suppose you roll a 16-sided die. Okay, so that basically means that this thing has the numbers 1 to 16. And this is not the case of just 1 to 6. And you're going to roll it 5 times and observe the number on the top of the die. How many possible outcomes are there for the 5 rolls? Well, let's think about this. Remember, you can just use the blanks. This is your first roll, second, third, fourth, and fifth roll. So you pick that up and say it's your turn, and you roll it, and you get 16. And then the second time, you get 16, and 16, and 16, and 16. So basically you have 16 to the 5th power. Now we're multiplying these because the events are independent. And your answer for this one is going to be 1,048,576. Okay, then it says, and how many of the outcomes in 1B do the 5 rolls produce 5 different numbers? Okay, so we're basically, you're going to do the same thing. You're going to do 5 rolls. And again, so the first time you have 16 numbers. Let's just say the first number we get was a number 1. So I can't use that number anymore. So how many numbers are over here? That means there's 15 numbers. And the second one I roll as a 2. That means there's only what? 14, 13, and 12. Okay. Basically, in this case, the order does matter. Order matters. And so what we're doing is from 16 numbers, we are picking 5 of those numbers. And remember your formula for permutations is npnk equals n factorial over n minus k factorial. And if you do that, you will get 16, 5, so 16 factorial over 16 minus 5 factorial, which would be 16 factorial over 11 factorial. So 16 times 15 times 14 times 13 times 12 times 11 times dot 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 dot. And then the denominator is 11, so same thing, 11 dot 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 dot. And then these will all cancel, so you're just left with this, which we already have over here. And if you multiply those numbers, let's just double check that. So I'm going to go to math, probability, NPR. Out of 16 numbers, go to the right, pick 5, enter 524,160. Pick the wrong one. 524,160 is our answer. All right, let's go on now to 7C. What's the probability that at least 2 of the rolls are the same? Now remember, when you see the word at least, the shortcut is to use what? The complement. The complement, let's write it out. The complement here is all the roles are different. That means none are the same. So first, we're just gonna, we did this back, I think, in example number 1. The first thing you want to do is you want to figure out the probability that all roles are different. So you have the total from 7A, which was 1,048,576. And then you can use the number from the previous problem because this is all different numbers. Does this make sense? And when you do that, you will get 0.4999. Okay, so then that means getting the probability that at least 2 roles are the same is just 1 minus the probability that all the roles are different. And if you do that, so that was 0.49999. Let's do that in black. You will get 0.50001. So again, for 7, we just used the complement. All right, question number 8. Dream Team. Mr. Picari often uses a computer program to randomly select 4 students from his class of 24 students to solve the problem on the whiteboard. How many possible teams of 4 students can be created from this class of 24? All right, here's the question we need to answer. Does order matter? Yes or no? If I'm just going to pick 4 random students and say, hey, go to the board, do the problems, there is no. So if order doesn't matter, then what are you using? You're using combos. So here's your total, and this is what I'm picking from. So I have C N K equals n factorial over n minus k factorial times k factorial. Do it by hand and then we'll check with calculator. So 24 and this was 4. So basically from 24 choose 4. So 24 over 24 minus 4 and 4 factorial. So this would be 24, 23, 22, 21, 20, dot, 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 dot. That one's going to be 20 factorial. And then you have the 4 factorial. Again, those will all cancel. And we will get 10,626 different teams. Okay, let's go ahead and look at the calculator. Math, probability, which is the 4th one, so go over. Number 3, 24, choose 4. 10,626. All right. One day, Mr. Picari poses a particularly challenging problem, and his random name generator produces a team of 4 students that includes 2 of the 3 top students in the class. You know, if you as Mr. Picari on his computer had the student who had the highest grade in the class, and the lowest person would be on the bottom. So the top 3 students, it would include 2 of them. What is the probability that a randomly selected group of 4 students will include 2 of the 3 strongest students? Okay, so whoops, try this one. Okay, so this is going to be a top student, right? That's the first one. So, and then this is also going to be a top student. That's the first, and then the third is going to be any other student. So I'm going to write not top student and not top student for the fourth one. Does that kind of give you a visual of what's happening? So here, between these two, there are how many top students? There are 3 of them. And I'm choosing how many of them? 2. So 3 choose 2. Okay, basically now, who is not the top? Who is not the top 3? Well, that's the bottom 21, right? Because 3 plus 21 gives me the 24 students in the class, right? Class 24 up here. So that means of the 21 students, I need to choose how many to go in there. Well, there's 2 spots, so that would be 21 choose 2. Okay, so if I wanted to calculate the total amount of combinations I can get, right? It doesn't matter if I got a top student, then non-top, then a top, and non-top. The order doesn't matter, so I can just multiply those. So 3 choose 2. I'm just going to use my calculator. Second entry, oh yeah, repeats. Delete, that'll be 3, choose 2. That would give you 3, and then repeat again. So second entry or enter, and then now I'm going to do 21, choose 2. 310. Okay. Okay, so this means number of ways to choose 2 of the top 3, there's only 3 ways. And number of ways to choose 2 of the remaining 21 students in class, there are 210, and if you multiply those, you will get 630. So basically, this is the probability. Let's write this out in words. This is the number of ways to choose two of the top 3. That's what I did in black. Let's change colors. And that's why I multiplied here. I should have used word first. And 2 of the remaining 21. Okay. All right. So let's review what we've done so far. This is the total number of ways of getting 2 of the top 3 and then 2 of the remaining 21. Okay, so how do I get a probability? Remember, a probability, pencil, are you working here? Probability is a fraction. So basically I want the total number of different teams, right? That's from the first top part question. And then the numerator is going to be the probability of what we just said. 2 of top 3 and 2 of the remaining 21. So that number is 630. And then the total different teams is above 10,626. If you guys put that in your calculator, you will get 0.059. Multiply by 100, you'll get a 5.9% chance. Okay? All right, last one. Based on your answer in AB, do you suspect that Mr. Picari rigged his random sample generator? Okay, this reviews an idea of when is it statistically significant. Statistically significant. And I'm just going to abbreviate that by SS. Okay? So when is it statistically significant? You like to say that all day long. The question is the probability, let's make note of that. We call that probability. There's another word because it's a fraction, right? Proportion, or super fancy word. They all start with what? P's. So they call this a p-value. Is the p smaller? Is it smaller than 5%? This is a general rule. Okay. If the answer is yes, then we would say it is yes, it is statistically significant. And then we kind of say we reject the original, or we call this the hypothesis, or something really fancy is they call this the null hypothesis. And if that number is smaller than 5%, we would say no. We would say not statistically significant. And then we would basically say, here's something fancy, fail to reject the null. And another fancy way of just saying someone fails to reject, that's just another way of saying accept the null hypothesis. Okay, so this is a big idea for statistically significant. We've kind of seen it throughout the year, but I just wanted to put out some kind of number. So my question is, what do you guys notice about our number about 5.9%? Is it smaller than 5%? The answer would be no. So we would say this is not statistically significant. We would just say that Mr. Picari, it sounds normal. It's not crazy to think so. So let's write that. Since there is a 0.059 probability of selecting a group of 4 from a class of 24. It's not odd, it's not suspicious, right? It is entirely plausible, possible. A sample like this arose due to chance. And what can you really do? You can just use a simulator and just keep testing this thing until you're super happy and you get to see more and more. Okay, that was question number 8C. We'll see you guys. Bye.
We doing math today. Ain't got time for no games. We doing math today. All work and no play. We doing math today. Listen up and behave. We doing math today. We doing math today.